Welcome back. So, now we were looking at the most important part of this study of lubricants on the silicon surfaces for micro electromechanical devices, and we said what is important here is to formulate the interface potential function, and we agreed that Lennard-Jones potential function is as good as what we can do with the 9-6 kind of model, and that did show some good results and good experimental ideas. So, we start with absorption. First situation here is absorption of the boundary lubricant. Once it absorbs, it essentially creates certain absorbed layers, and on top of that you have other layers which are non-absorbed layer. So, what we want to understand is how we can design again these boundary lubricants. So, as we saw again in this picture, that once we put more lubricants and if you have one surface, then essentially it has a stacking of the lubricant layer on top of the silicon surface. And remember, this is 001 surface which we are looking at, and if you look at this layer, what you see that after certain layers the lubricant doesn't have any effectiveness because it essentially stacks up. So, the adsorbed layers, the layers which are absorbed in the system are the one which is more responsible for the boundary lubrication in the micro systems. Now, we look at this model about two shearing planes. So, in this case we have this system, and I need to explain here the white atoms are silicon and the blue atoms are carbon and red atoms are hydrogen. Dodecane layer, this is the lubricant material, and what you see when you compress it, essentially it has much more disordered layer, but absorption happens on the top layer and the bottom layer. So, if you look at on the right hand side, these green atoms are non-absorbed ones, the blue atoms and the red atoms, these are the absorbed. If you look at the green ones are the non-absorbed. So, they are essentially connected with the blue atoms which are absorbed. So, now what we are going to do is provide some shear. So, this is the picture that you have been seeing in all my the lecture slides at the beginning. This is where it came from, where we looked at the two layers of the silicon, and then the green layer which is the non-absorbed and blue layer is the absorbed layer. So, what we saw is that as you shear, so we are going to make more shear. So, this is 1.54 angstrom sliding. So, what we are doing, the way we shear it, by once they get absorbed after equilibration, which you saw in the previous slide, now we are going to shear it. Now, we are going to move it by 1.54 angstrom. So, slowly moving, we are going to look at where the stress and strain develop in this shear layer. So, if we look at here, we increase the shear by 4.61 angstrom, and as you know, the angstrom distance between these atoms is very small, about 2.9, 2.8. So, we have essentially moved it by almost 2 lattice spaces, and what you see is that the absorbed layer remains with the top layer, and this absorbed layer also remains with the bottom, but the one which is in the middle is essentially shearing off. So, the shearing off is happening at the non-bonded level. So, let us give a little bit more shear. So, now you can see that the top layer is sheared off completely, and in this we also did a lot of studies on how the stress and strains are distributed. What we found is that absorbed layer with the dodecane on top layer and the bottom layer is essentially breaking off first at the non-bonded, which is expected as we move forward, but we also see is that there is also breaking off some of the hydrogen bonds at the bottom, that you can see with the carbon hydrogen chain. So, with higher shear, we are looking at the shearing happens on the middle portion of the lubricant. So, the lubricant has solid like structure which is bonded with the silicon structure and bottom structure, but if the layer becomes slightly thicker, that means there is a non-bonded part, then you start losing the lubrication because there is a sliding effect. So, the sliding effect happens at the middle layer where there is a non-bonded layers of the hydrocarbon. So, based on this we came up with some conclusions that the MD study shows that dodecane absorption on silicon 001 surface prefers to lie along the surface ledges, which is in agreement with our experimental data that we looked at using laser Raman spectroscopy. So, we had also done experiments on silicon surface with dodecane layers, and we shot the laser Raman spectroscopy and looked at what in the polarized Raman what kind of surfaces and ledges it follows. So, what happens that there are steps, and those are called ledges. So, if you look at in the step, you have a step, then ledge, then step, then ledge. So, if you look at hydrocarbon, the reason it is kink, creating a kink, because it is following the ledge. So, when it comes to the next ledge, it will turn and then go to the next ledge of the silicon material. Now, this would not be available unless we look at the atomic camera, atomic level. We did not know that ledge is so important for the creation of the hydrocarbon lubricant. Now, if you go to at higher concentration of absorption, we saw that the molecules stand up, they stack up, and the layer close to the silicon behaves solid like, while the layers on the middle they behave liquid like. So, while the solid lubricant and the what we call as boundary lubricant has to behave solid like, which is a preferred model, the liquid like layer provides lot more overcoming the friction. So, you do want certain liquid like layer present, while you want to make sure you do not lose the solid like behavior of the layer which are boundary lubricated. So, now if you look at we also looked at the stability under the shear. So, we found that the stability of silicon surface depends on the shear of the middle layers of the absorbent hydrocarbon. So, if we have to say that a particular hydrocarbon needs to stay and it has to be stable, so that it does not shear off those layers, which is the problem we started with, then we need to design a lubricant which has higher shear modulus again for the middle layers. So, now dodecane is one kind of design, but now we can play with the design in a way that we get much higher shear values for the middle layers, and then it will stay there. And that is how we can design highly sophisticated lubrication system based on the atomic understanding, molecular dynamics understanding for micro electromechanical devices.